Good morning, everyone. Today we are diving into one of the most fascinating areas of fluid mechanics, that is the flow over immersed bodies. Think about an airplane that is soaring through the sky, a fish gliding through water, or even the wind whistling past this building right now. What do all these have in common? They are all examples of external flows, situations where a fluid completely surrounds an object. So, in this particular topic, we are going to explore what happens when the fluid interacts with the objects. And here is the exciting part. By understanding these concepts, you will be able to explain why golf balls have dimples, why airplanes don't fall out of the sky, or even why your car's fuel economy drops at high speeds. So today's focus will be on the general characteristics of the external flow, specifically looking at the lift and drag concepts and how the nature of the flow changes depending upon the conditions. So let us start with the very big picture. When we talk about the external flows, we are dealing with the objects completely surrounded by the fluids. The applications are everywhere, such as in the aerospace, the airflow around the airplanes, helicopters, and even falling snowflakes. Then we see the automotive industry, where the aerodynamics of the cars, the trucks, and the bicycles crucial for the fuel efficiencies. So we have the marine application where the water flow around the submarines and the ships, and then we have the civil engineering part where the wind effects on the buildings from your house to skyscrapers. Now here is an important distinction. Sometimes the objects move through stationary fluid, like an airplane flying through calm air. Other times the fluid moves past a stationary object like wind blowing past your dome building. Mathematically, we can make these situations identical by fixing our coordinate system to the object. We will assume the upstream velocity is uniform and constant, even though in reality the wind is often gusty and turbulent. But for our purposes, that simplification works well. So before we dive into forces, let us look at how we classify bodies in the external flows. This particular figure shows three different categories. First is a two-dimensional object. These are infinitely long with constant cross-section. Now I know what you are thinking, that nothing is infinitely long. You are absolutely right, but many objects are long enough that end that the end effects are negligible. Think of a long bridge, pier, or an infinitely long wing. We can analyze a cross section of it and get the meaningful results. So, a second one of this particular figure are the axisymmetric bodies. These are formed by rotating a cross-sectional shape about an axis. A submarine hull or a rocket body fits here. The third figure shows the three-dimensional body. These may or may not have symmetry. Most real objects fall here. So we also classify bodies as streamlined or the blunt. Streamlined bodies like aircraft wings or racing cars have minimal effect on the surrounding fluid. Blunt bodies, on the other hand, like parachutes or buildings, dramatically alter the flow. So generally, but not always, it's easier to push a streamlined body through a fluid than a blunt body, one of the same size. Now, let us go to the heart of the matter, the forces. When any body moves through a fluid, interaction occurs at the fluid-body interface. These forces come from two sources. Wall shear stress, which is the tau W, due to the viscous effects acting tangentially to the surface, and the second one is the pressure force, P, acting normal to the surface. So both vary in magnitude and direction along the surface. Sometimes we need the detailed distribution, but often we only care about the integrated result. The resultant force in the direction of the upstream velocity is called as a drag and is denoted by the capital D. The resultant force normal to the upstream velocity is called as the lift, which is denoted by the capital L. So for three-dimensional bodies, there might also be a side force perpendicular to both. Now look at this particular exam figure, part C in your mind's eye. The drag and lift are the net result of all those tiny pressure and shear forces acting on every bit of the surface. So let us get mathematical for a moment. Don't tune out. This is important. For a small area element dA on the surface, oriented at some angle theta, we can break the forces into components like the x component, which is the drag direction, and the y component, which is the lift direction. So we write the particular equations as represented over here. Then we integrate over the entire surface, and we get the drag and the lift forces like these. So notice something crucial in this, that both pressure and the shear stress contribute to both lift and the drag forces unless the surface is perfectly aligned or aligned with or perpendicular to the flow. For a flat plate parallel to the flow where theta is 90 degree on the top and 270 degree on the bottom, the pressure forces cancel only the shear stress contributions to the drag. But when the flat plate normal to the flow, we are analyzing such a case in which theta is equal to 0 on the front and 180 degree on the back. Shear forces cancel each other, only pressure contribute to the drag. So this is why a flat plate held parallel to the wind experiences much less resistance than one held perpendicular. So you have all felt this. You might have all felt this. So now, since getting detailed pressure and shear distributions is incredibly difficult, both theoretically and experimentally, we use the dimensionless coefficients over here. So we use CL and CD as the coefficient of the lift and the drag, in which A is the characteristic area in these both equations. But which area? The question is that which area we have to take. It depends upon the situation actually. Sometimes we use the frontal area, the projected area seen from the upstream, like the shadow you had cast if a light shone from the flow direction. Other times we use the planform area, the area seen from the above, like looking down on an airplane wing. So the key point is always note which area is being used when you see drag coefficient data. Now moving forward, Reynolds number is very important for the characteristics of flow path and object. Now for the second part of our discussion, how does the flow actually behave? The character of the flow path and object depends strongly on various parameters like size, orientation, speed, and fluid properties. According to the dimension analysis, and the key dimensional parameters are the Reynolds number, the Mach number, and the Froude number as displayed over here. So for now, we will focus on the Reynolds number effects. Why? Because it fundamentally determines whether the flow is dominated by inertia or either the viscosity. Most familiar flows involve moderately sized objects from centimeters to meters moving at moderate speeds through air or water. This gives us Reynolds number roughly between 10 s to the power 1 to 10 s to the power 9. So rule of the thumb is that when Reynolds number is greater than 100 means that the inertial effects dominate, and when the Reynolds number is very less than 1, it would mean that the viscous effects dominate. So most everyday flows are inertia dominated, but there are important exceptions also. Tiny particles settling in a lake or objects moving through thick oil experience low Reynolds number flow where viscosity rules. Now, moving towards the flow evolution with the Reynolds number, let me show you how Reynolds number transform the flow. So let us look at this particular figure in your mind. Flow past a flat plate at different Reynolds number. When the Reynolds number is equal to zero point 0.1, is equal to the value of 0.1, at very this very Reynolds number value, viscous effects are strong and felt everywhere. The plate affects the flow far ahead, above, below, and behind. So you have to travel far from the plate to find undisturbed flow, and the streamlines are significantly displaced. But when the Reynolds number is equal to 10, as the Reynolds number increases to the value of the 10, the region where the viscous effects matter shrinks in all directions except the downstream. You don't need to go far ahead or to the sides to escape the plate's influence. So streamlines are less displaced in this case. But when the Reynolds number is very large of the value of 10 is to power 7, we encounter a completely different world. Inertia dominates in this case. Viscous effects are negligible everywhere except in two places. What are two places? The first is a very thin region next to the plate called as a boundary layer. Here, the velocity changes from zero at the wall, which is hereby called as a no-slip condition, to nearly the free stream velocity. The thickness sigma grows with the distance x from the leading edge but remains much smaller than the plate length. And secondly, a relatively thin wake behind the plate. So outside these regions, the fluid behaves essentially as if it were inviscid, which means no viscosity effects at all. So this boundary layer concept proposed by Ludwig Prandtl in 1904 revolutionized the fluid mechanics. It's why we can analyze complex flows by dividing them into viscous and inviscid regions. Now we have to move forward to the blunt body flow patterns. Now look at this blunt body, a circular cylinder. The story gets even more interesting over here, that when the Reynolds number is equal to zero point 0.1, equal to the value of zero point 0.1, at this very low Reynolds number value, the viscous effects are felt many diameters away in all the directions. Surprisingly, the streamlines are symmetric front to back. The pattern in front of the cylinder looks the same as behind it, but when the Reynolds number increases, the viscous region ahead shrinks and the flow loses its symmetry. And sometimes something remarkable happens, that the flow separation occurs. At some point in the on the cylinder, the fluid's inertia prevents it from flowing the curved surface around to the back. It detaches, creating a separation bubble where the fluid actually flow backwards. So another case is that when the Reynolds number value is very large, so at still larger Reynolds numbers, the viscous region is forced further downstream. We get a thin boundary layer on the front portion and an irregular, unsteady wake extending far downstream. So outside the boundary layer and the wake, the flow is essentially inviscid. So here is the mind-bending part, that the fluid viscosity is the same everywhere. Whether the viscous effects matter depends entirely on where you are in the flow field. Inside the boundary layer and the wake, the velocity gradients are huge, so shear stress mu times the velocity gradient is very significant. Outside these regions, the velocity gradients are small, so viscous effects are negligible. Now, why separation happens? To understand the separation effect, think of a bicyclist coasting down a hill and up the other side. So with no friction, the rider could start from the rest, coast down, and reach exactly the same height on the opposite side, exchanging potential energy for kinetic and back again. So, but with the friction, rolling resistance, air drag, the rider loses energy. They can't make it as high on the opposite hill. So in fluid flow, the fluid particles in the boundary layer experiences the same pressure distribution as those outside. They have to climb the pressure hill on the rear of the cylinder, but because of the viscous losses, they don't have enough energy to make it all the way. They stop the flow. The flow separates, and we get the reversal flow. This separation dramatically alters the whole pressure distribution. The average pressure on the rear becomes much lower than on the front, creating the pressure drag, even though the viscous shear stress itself might be tiny. So this explains the D'Alembert's paradox that the inviscid theory predicts zero drag, but real fluids, no matter how small the viscosity is, it will produce a drag because of the boundary layer separation. Now, here is where we are headed into our next lecture. Um, Notice in this particular figure, part C, at a very large Reynolds number, the flow organizes itself into distinct regions. The boundary layer, which is the thin region next to the surface, becomes the key to understanding everything. So within this boundary layer, the flow can be laminar, smooth and orderly, or it can be turbulent, chaotic with intense mixing. The transition actually depends upon the Reynolds number based on the distance from the leading edge, typically occurring around Reynolds number in the extra. Rex equals to 5 multiplied by 10 is to the power 5. So a turbulent boundary layer is thicker, has a fuller velocity profile and produces higher wall shear stress. But interestingly, for blunt bodies, a turbulent boundary layer can delay separation, reducing pressure drag. So this is why golf balls have dimples in it. So next time we will be exploring the boundary layer characteristics. We will learn how to define the boundary layer thickness. It's not as straightforward as you might think. The difference between the displacement thickness and the momentum thickness, the Blasi solution for laminar boundary layers, and how to calculate the shear stress on and drag on the flat plates, and what happens when the boundary layer becomes turbulent. So we will see how Prandtl is brilliant insight, allows us to analyze the complex flows by focusing on this thin region where viscosity really matters. So for today, what we have discussed up till now has the drag and the lift that come from both pressure and the shear stress distributions. The Reynolds number fundamentally determines the flow character, and at high Reynolds number, the flow divides into boundary layer and inviscid regions. We also saw that the boundary layer separation creates pressure drag and explains the D'Alembert's paradox. So it's all for now. Uh, Thank you for your attention, and we will see the next topic, which is about the boundary layer characteristics in the next section. Thank you.